This lesson's about work. You'll be able to define work and find the work done by both a constant and a changing force. Up till now, we've been thinking about the motion of an object by talking about forces, but we can now change to thinking about energy, and energy can often make difficult problems when we think of them from the perspective of forces much easier to deal with. But to do that, we need to define energy. Let's back up a step and define work first. When a force acts on an object and that object moves through a displacement, we say that work is done. And work is the product of the force and the displacement. However, work is only done by the component of the force that's parallel to the displacement. So imagine you have a situation like this, where you are pulling a box, and that box is moving through some sort of displacement in this forward direction, but instead of pulling it on the horizontal here, you're pulling it diagonally like that with a force applied at an angle. Well, not all of your force is doing work on the block. Only the component of the force that is parallel to the displacement is doing work. If we take a look at the diagram here on the right hand side, if this is our displacement and that's our force and there's an angle of theta in between them, we want to find the component of the force that's parallel to the displacement. That can be called F parallel, and it's equal to F cos theta by our mechanism of taking components. So if we want F parallel, which is F cos theta, to be multiplied by our displacement to find work, then we write that as F, the magnitude of our force, multiplied by S, the displacement, times cos theta, cos of the angle in between them. And we often put the cos theta at the end. So that's our formula for work. Here's a question to consider. Does the Earth do work on the moon, assuming that the moon is in a circular orbit around the Earth? So here's our Earth in the center, and we have the moon going in a circular orbit around it. Well, the force that the Earth is exerting on the moon is a gravitational force that is operating along the radius of the moon's orbit. This is the force, but the displacement that the moon is experiencing is always tangent to that circle, that circular orbit. So the force and the displacement are at right angles to each other. In other words, theta is equal to 90 degrees, and cos theta in this case is therefore equal to 0. So work, which is Fs cos theta, is going to be equal to 0. The Earth is not doing any work on the moon because the force that the Earth exerts is always perpendicular to the displacement that the moon is experiencing. Note that work is a scalar, not a vector. We can talk about positive or negative work, but work doesn't have a direction. And the unit of work is the joule. 1 joule is equal to 1 Newton meter, a force of 1 Newton exerted through 1 meter. Similar to the case with individual forces and the net force, we need to be careful to distinguish between the work done by an individual force, for example, the applied force, the force of gravity, and the work that they do, and the net work done by all forces. Let's take a look at an example with a constant force. We've got a block of weight 20 newtons that's being pulled through a displacement of 2 meters at constant speed on a horizontal frictional surface, and there's an applied horizontal force of 15 newtons. We're asked to find the work done by individual forces. Let's draw a free body diagram first. We have a force of gravity of 20 newtons, and therefore we must have a normal force of 20 newtons because it's not accelerating in the vertical dimension. We have an applied force of 15 newtons, and again, because it's moving at constant speed, not accelerating, that means that we must have a frictional force of 15 newtons in the opposite direction. So there's our free body diagram. We're also moving through a displacement of 2 meters. First, we're asked to find the work done by gravity on the block. Now remember that work is equal to the component of the force that's parallel to the displacement times the displacement, or Fs cos of theta, the angle in between them. Well, in the case of gravity, which is operating downwards, and the displacement, which is forwards, gravity is perpendicular to the displacement, and therefore the angle theta in between them is 90 degrees, and cos of 90 is equal to 0. So no work is done by gravity on the block, just like we saw in the Earth-Moon example. Similarly, the normal force is also perpendicular to the displacement, and so by the same argument, no work is done. The applied force, however, is parallel to the displacement. It's in the same direction, and in this case, theta is equal to 0, and cos of 0 is equal to 1. So our formula becomes F, which is 15 newtons, multiplied by S, which is 2 meters, multiplied by 1, and that gives us a total work of 30 joules done by the applied force. The frictional force operates in the other direction. Now theta is equal to 180 degrees, and cos of 180 degrees is equal to -1. And so, although we have the same magnitude force and the same displacement, that's multiplied by -1, and we have -30 joules of work being done by the force of friction. So although work is a scalar, it doesn't have a direction, we can still have negative work. Now if we take a look at all the different forces and the work that they do, and we add them up to find the net work, we find that there is a net work of 0 joules done on the block, because the negative work done by the force of friction cancels out the positive work done by the applied force, and gravity and the normal force aren't doing any work at all because they're perpendicular to the direction of motion. Note that there's two different ways we could have found this work. What we did, which was we found the work done by each force individually, and then we found their vector sum, we added them up, or we could have found the net force first and then found the work done by that. If we go back up here, the net force is equal to 0, and so we could have found that net force, and then the work done by a net force of 0 would be a net work of 0. So that's an example with a constant force. What about when there's a changing force? Well, when there's a changing force, this formula doesn't work very well because the value of the force is changing. So we can't use it. Instead, what we need to do is graph force versus position, as is shown here, and then the work is the signed area under a force position graph. Just like earlier we found that the displacement is the signed area under a velocity time graph. So here's an example. This one has an area that's relatively easy to compute if we break it into these 3 sections. The area of this triangle is 20 joules. Newtons times meters gives us joules. In this one, this rectangle also has an area of 20 joules, and this triangle has an area of 30 joules. So if we add those 3 together, then we get a work of 70 joules. Positive because it's above the position axis. So that's an introduction to work and how to find work with a constant force and a changing force.